Our blood maintains a stable pH level even when we consume acidic soda or sour food, thanks to a remarkable system called a buffer solution. The sturdy buffer castle flawlessly protects the stable pH of our blood. On top of these castle walls, two types of specialized soldiers stand side by side for a perfect defense: the weak acid soldiers and the conjugate base soldiers. There is a clear chemical reason why buffer solutions are made of weak acids instead of strong acids. If the soldiers guarding the walls were strong acids, they would completely dissociate into their ions. With all their hydrogen ions gone, they have nothing left to defend the castle when real enemies attack, rendering them unable to fight. On the other hand, the weak acid soldiers are very calm. They do not release their hydrogen ions recklessly. Instead, they hold them tightly and quietly maintain a state of equilibrium through partial dissociation. By saving their hydrogen ions during normal times, they safely maintain the peace inside the castle by keeping the pH completely stable and only selectively use them to defend when a lethal enemy appears. The weak acid soldiers truly shine when the blue army from outside the castle, the strong bases or hydroxide ions, attacks. As the blue soldiers try to climb over the walls, the weak acid soldiers step forward without hesitation and release their saved hydrogen ions. When these hydrogen ions meet the hydroxide enemies, they undergo a perfect neutralization reaction. They combine together, completely losing their toxicity and transforming into pure, harmless H2O water. It is the moment the threat is completely washed away. The buffer system doesn't just defend against bases. Powerful acids, essentially an oversupply of hydrogen ions, also attack the walls. If their concentration rises, the castle's pH balance will collapse into an acidic state. Here, the conjugate base soldiers step in. As proton acceptors, they capture the invaders. When a conjugate base binds with an invading hydrogen ion, a chemical equilibrium shift occurs. Chemically, the conjugate base A- reacts with the hydrogen ion H+, transforming into a stable weak acid molecule HA. This neutralizes the acidity-raising enemies by turning them into allies. Even as hydrogen ions pour in, ample conjugate bases are standing by. Following Le Chatelier's principle, they continuously bind and lock away the ions as fast as they arrive. This keeps the free hydrogen ion concentration inside the castle completely constant. Weak acids act as proton donors, while conjugate bases act as proton acceptors. Thanks to the precise coordination of this reversible reaction, the sturdy buffer wall withstands any attack and maintains a steady state. How do we actually make these buffers in the lab? There are two main methods. First is direct mixing. We simply mix a weak acid with a salt containing its conjugate base. For example, mixing acetic acid with sodium acetate. Second is partial neutralization. We add a strong base to a weak acid, but exactly half the amount. Here, the strong base acts as the limiting reagent, meaning it is completely consumed once the reaction is over. The added strong base disappears without a trace, but in the process, it converts an exact equivalent amount of the weak acid into a newly formed conjugate base. As a result, the strong base is entirely gone. What's left in the solution is half of the unreacted weak acid and the newly generated half of the conjugate base. This creates a perfect 1-to-1 ratio of weak acid and conjugate base, achieving a state where the buffer's defense capability is at its absolute maximum. What about maintaining a pH above 7 with a basic buffer? The principle is exactly the same, but we use a weak base and its conjugate acid. We can directly mix ammonia with ammonium chloride or partially neutralize ammonia with a strong acid. Whether acidic or basic, achieving this 1-to-1 ratio is the ultimate secret to a highly stable buffer system.